Good afternoon. Welcome to another Science session in Rupert College on the third Sunday of this month. And today we have a speaker who doesn't need any introduction. All of you know about him, but still I will say something about this person. Arnav is the person who is behind this whole program of Science. Obviously, I know him because he's a professor. He was a professor in my department.
I still am.
Yeah. But now he is in charge of Homi Bhabha Center for Science Education, which is a center of PIFR related to science education. He's the director of that center. Today he's going to will be talking about something, science of the climate change. I don't know. I have never heard Arnav speaking about climate change. So, but I hope it will be interesting, as always, Arnav's talk is. So, welcome you, Arnav, in your channel.
Thank you. First thing, online audience, I hope you can hear me. If not, please put it in the chat. Also, if you have questions and comments, please put it in the chat. Otherwise, there is no way I will know. We have somebody monitoring the chat, the YouTube chat, so they can either interrupt me and ask questions, or we can take them at the end of the talk, whatever. But please put your questions and comments in the chat. And as Dippo said, thanks for introducing me. I have never spoken on this before. And before we start, let me share my screen. This is something I should do. So for the benefit of the online audience, let's first share screen. Share. Okay, come. You don't have to leave your shoes outside. Just come in. Okay, so now I hope, online audience, you can see my screen, and I hope it's visible on YouTube as well. Okay, so I'm going to try to tell you a little bit about climate change. Hopefully you've heard these words, and see how it goes. So I must tell you that I am not an expert in weather, climate, meteorology, geophysics, anything concerning, I'm not a professional working in this field. And the most important thing, as I have been reading up about this, is that many of the issues are actually beyond just science. There are several social issues, political issues, ethical issues that come into this, which are going to complicate the picture a lot. So we have to be a little careful when we discuss all these things. I have hopefully a lot of interesting stories to tell you. I'm a storyteller, as you know. And if you want to find out more, obviously the formal government systems of the world are very, very concerned about this. So you can look at what is called the IPCC, the Intergovernmental Panel on Climate Change. These are the guys who won the Nobel Prize, Peace Prize, something a few years back. There is also the United Nations, which has a whole chapter on climate change. In fact, they have what are called these COP, the COP meetings. There's one coming up next month in Baku in Azerbaijan. There was one in Dubai last year. Anybody knows what is COP? Conference of the Parties, and this is organized, it's called the United Nations Climate Change Conference, normally called Conference of the Parties. These are parties who are signatories to this. There's also the United Nations Framework Convention on Climate Change. In India, we have the Ministry of Environment and Forests, which is now the Ministry of Environment, Forest and Climate Change. There is like you had the NEP for education, there's also a national environment policy. Actually, the motto of the MOEFCC is actually very good. It says, nature protects if she is protected. So I think that's a very, very nice statement. Of course, beyond this, if you really want to get, in brief, succinct information, there's nothing better than going to NASA's climate change page, science.nasa.gov climate change. Within India, the institute that works most on climate change is the Indian Institute of Tropical Meteorology. And there, in particular, there is a climate research lab, and it's a climate change also they study. The scientist in charge, Roxy Call, very well recognized. And you can see his website. It's Roxy, ROCKSEA. He's on Twitter on the same thing. beautiful examples and explanations and lectures, etc., that are available. So, they've said a little knowledge is a dangerous thing. So bear with me. I have very little knowledge on this. I'll try to share a smaller part of that with you. So my aim today, I'll be very happy if I can convince you based on evidence that global warming is real. It's happening. It's here. Okay. The second thing is I will try and look at what I call big history, not history as in the history textbook, which is history of human history, but history of the planet on a much longer time scale, to see why we are at this stage where we are. Okay. And then, I think you've heard that the big problem is, this carbon and carbon dioxide. I don't know, why is carbon dioxide the culprit? We'll try and look at that. At the end of it, if I can make you reflect on the fact that this is a very serious problem and it's very complicated, it's not easy, I think that will be good. And I will say upfront that I have a physics/engineering background, and some of my biases will probably show in the way I look at data that is available. So I look at it in a perspective that is now. Let's look at what is just happening around us locally. Let's not worry about the world and all that. Let me ask you: do you feel that there is a change in climate? Okay, this is like the weather around us over a long period of time, not the political climate if you read the newspaper, or the investment climate if you read the business page. But right here in Mumbai, do you feel over the years the climate has changed? Okay, and has it happened in India? Has it happened in the world? But let's look at it in Mumbai. Do you think Mumbai, today is the 20th of October. Last night it was raining. Was it raining last night where you were? Is that the typical monsoon of Mumbai? There was lightning and thunder last night. Right? I think just in Mumbai, please let me know if there are, please put, online audience, please put your comments in the chat. We can have this discussion online as well. Do you feel that there's anything else that has changed over the last, say, 20, 30 years if you've been around? For those who have, yes? The winters are getting warmer. Right, you barely ever need I don't think I used even a chadar last year in Mumbai. Never had very strong winters, but still, it's okay. That's one thing. Cyclones, there are more cyclones. Okay, yeah, that's one observation. There are more cyclones. There are short bursts of rainfall. The variability and intensity of rainfall. Very good observation, ma'am. There. So earlier there was a continuous period of rain in the monsoon. Now it is more erratic and much more heavier whenever it rains. Okay. The monsoon start is delayed, and hence the end is also probably. Yeah. The funny thing is I think the Weather Bureau has said that the monsoon has ended, but it doesn't look like. Okay. Anyway, now. First thing, I want to ensure we understand what is weather and what is climate. Okay, so how hot it is today, whether it is going to rain today, tomorrow, etc. Short-term things are weather. Long-term averages are climate. Okay, climate generally is 30-year average at least. You average over 30 years, that is climate. If something is happening tomorrow, we are predicting the weather. We are not predicting the climate for tomorrow. We are predicting the weather for tomorrow. And in Mumbai, you'll notice that often it's raining very heavy today, the next day they declare a holiday. Right? That's because in Mumbai, it's often very safe to predict that tomorrow's weather is like today. It's not like other places where there are very drastic variations possible from one day to the other. It's often that tomorrow is like today, which is a very safe prediction to make in Mumbai. Right? So, of course, these days with satellite images and a lot of data that's publicly available, you should be able to make better predictions, but still. Now, let us just look at the climate of the world. And by climate, what I'm going to show you are 30-year averages. Typically, the baseline is taken 1950 to 1980. 1951 to 1980. Okay. You can come in front, if you want, no problem. So climate depends on many things. Climate depends on where on the globe you are. Latitude, longitude, altitude, terrain. Are you in a valley? Are you somewhere else? Are you near the coast? because the oceans have a big effect on it, land breeze, sea breeze, etc. There are ocean currents, which could be warm currents or cold currents. Land use, are you in a forested area, are you in a barren area? All these things will affect the climate. Now, in general, so what you're seeing in this image is the average monthly surface temperature from, let's say, 1961 to 90, again a 30-year period. And in general, blues are colder, reds are hotter. So what is happening is August, September, October, moving into winter, cold in the northern hemisphere. The southern hemisphere is getting warmer. And as it becomes summer in the northern hemisphere, it's getting cooler here. The blues are going up, again it comes down. So this is the cycle of climate. Okay, this is just what you're seeing is temperature variation across the globe through the year. Okay. Just like we can look at temperature, we can look at rainfall. So if we look at average monthly rain, well, near the equator, it rains all through the year. So that's not surprising. Dark blue is more. Okay, that's the monsoon. The July-August thing is going to be just wait and you'll see the monsoon come here. So December, January, you can see barely the little bit of rain in the thing. May, June, the monsoon starts. July, the monsoon is all over India. August, all over India. September is still there, and then the monsoon goes away. And then November, December, there's a little bit of monsoon over there. Okay. And you can see how the rainfall pattern varies across the globe. Again, this is 1961 to 1990, long-term average. This is climate. Now the claim is that the climate has been changing over the years. Okay. And this is the long-term climate, that is what is changing. And the amazing thing is today, data visualization can be done in many, many ways. I'm going to show you 3 different videos or graphs or whatever you call them. 3 different ways of visualizing this. Okay. Now, you saw that, you remember the graph where every month you had some average surface temperature. So I can work out what is the average surface temperature every month. Okay. And I can plot it on a circle. I'll plot the temperature January, February, March, April, to make a circle. Okay. And I'll plot these circles for every year from 1880 onwards. Okay. Let's do that. So in the middle, this is like a 0. This is the average from 1951 to 80. So initially, before that, they're mostly cooler than the average. Watch. The color in which the year is written is also an sort of example of this. So we can take all those things, line them up, and see that clearly from the 1880s till now, there has been a gradual increase, and this increase is increasing right now. The temperatures are going up. Okay, this is one. You can go to another way of looking at it is, again, this is compared to 1951 to 1980s. You take groups of 5 years and see the average temperature over 5 years and see how that is varying across the globe. So again, do you see after the 1980s especially, we're going more towards the yellows and reds. There is an overall warming. This was globe as a whole. You want to watch this country-wise. I mean, data visualization people are real cool. I mean, these are very, very cool videos. Here's another one. What you're seeing is, this is a list of countries of the world. Okay. This was their average temperature compared to the mean temperature in a particular year. Just if you want to note, India is here. India is in Asia. So this is Asian countries, European countries, American countries, Australia, Africa. India is over here. This is India. Okay. So what we're going to see is how do these temperatures vary across the years for individual countries. So there are always random variations. Let's just run this. I'll take your question. This was till 2016. But again, as you can see, we started with mostly bluish things and we landed up with red things. There was a question, yes. You can also see some variation in World War II, but that's probably irrelevant. I mean, right now we're looking at much longer term things. Okay. So as you can see, individual countries have also, especially if you notice in the late 1990s, early 2000, Europe was getting much hotter than other places. So there are places which have been experiencing this much more than others. So this is again a visualization of this long-term climate that is changing. Okay, this is the Indian picture. This is temperature change in India again from 1901 to 2020. As you can see, in the last 20 years or so, the temperatures have been always above average. Always above average. Okay. Now, there are a lot of things that have changed. Apart from the temperature, that is one of the things. The global temperature has gone up 1.4 degrees since the era of pre-industrialization. Carbon dioxide has changed. Methane has gone up. The amount of Arctic sea ice has gone down. Ice sheets that cover land have gone down. Sea level has gone up. The oceans have gotten warmer. Okay, this is NASA's sort of vital signs of the planet. We look at each one of them in detail. Somehow everybody seems to worry about carbon dioxide. So this is the current measurements of carbon dioxide, that there is 0.4%, 4222 ppm of carbon dioxide. So there are two ways of measuring it. From 1958, we have direct records of measurement. I will come to this particular curve. It's been called the most important curve of the 20th century. We look at this in detail. But from we are measuring in Hawaii, they've been, and other places, they've been measuring the amount of carbon dioxide in the air, and it's going up. Okay, but we know what happened before this also indirectly by looking at ice core samples. There is ice that has accumulated in the Antarctic and other places where you can dig 1 kilometer of ice, extract it, you know how the ice fell, and you can see how much carbon dioxide is dissolved in it. From that, you can calculate up to 800,000 years ago what was the amount of carbon dioxide in our air. And you can see it has been fluctuating. It has been fluctuating. It's certainly fluctuating, but it has never been above 300 ppm until we came to 1911, and then the rise is very, very sharp, and now we've crossed 400 ppm. Okay, so the yellow part is ice core data, and from 1958 we have actual data, but it matches. So carbon dioxide has gone up, and that particular curve, and you can also look at it this way. This is, if you look at this part, this is where the industrial revolution starts, and it starts going up, and then it shoots up. Okay, so this is a very important curve. It's called the Keeling curve. The Keeling curve is, what did I do? It's called perhaps the most important scientific graph of the 20th century. Charles Keeling, he was employed at the Scripps Institute of Oceanography. 1957-58 was the International Year of Geophysics, and they had money to build a couple of stations to monitor carbon dioxide. They built one at the South Pole and one on top of a mountain in Hawaii. The South Pole one, unfortunately, they did not get funding and closed down after a few years. The one in Hawaii is running since 1958. After his death, his son has been continuing to run these measurements. He died in 2005. And this is sort of the most, we have continuous measurements over the years from 1958 till now about the amount of carbon dioxide. Please note that this curve goes up, down, up, down, up, down. And this is the seasonal variation. You have a 6 parts per million season variation because much of the land is in the northern hemisphere where there are plants growing. When plants grow, they absorb carbon dioxide. And of course, there's a lag. Carbon dioxide is being generated. By the time the plants grow, so you see a dip in carbon dioxide because of plants absorbing it. Then again, when winter happens, they shed their leaves and everything else. Those things have gone. There's no absorption happening. It goes up. So this is a seasonal variation. Okay, but it's a very, very beautiful data saying that the carbon dioxide levels have gone up. We'll see why carbon dioxide much later. Then you have methane. Methane is another gas that is responsible for trapping heat, and these are the levels of methane sampled from various places. And again, we are almost at 2 ppm methane right now in the air. Okay. Per volume. If I take X liters of air, how many parts of it is going to be carbon dioxide or methane or something like that? The question was, what is parts per million or parts per billion? It's by volume, volumetric measurements. Okay. Now, there is the sea, the oceans, the ocean actually, it's all connected. And near the North Pole, the Arctic, the South Pole is on land, it's on Antarctica. The North Pole is in the water, it's the Arctic Ocean. And there the Arctic sea ice freezes. Now, the amount of ice that is forming is decreasing with time. So the amount of Arctic sea ice, the million square kilometers of sea ice is also decreasing. Okay, and you can see pictures of this as well, saying that this was the amount of sea ice September 14, 1984 and September 13, 2012. Much less of the sea is frozen. In fact, in the last few years, earlier there was a problem. You needed icebreakers to clear a path between if you wanted to get from here to Asia. But now there is all-weather shipping zones routes available because there is no ice. There are ice sheets on land. So this is Antarctica and Greenland. They have the most amount of ice on land, and that ice is also melting. Antarctica is losing about 150 billion tons a year. Greenland is 270 billion tons a year. That ice is melting and going into the sea, which obviously means there's more water in the sea. Sea levels are going to rise because of ice melting. So it's about 140 billion tons per year. Glaciers on land are going back. This is the Gangotri Glacier. This is very old data from the 1780s, 1800s, 1900s, 1996. The glacier, the Gangotri Glacier is going back. Okay. I will show you my own data, my own picture on global warming. Okay. Just for fun. I went to Switzerland in 1999 and I took that picture. My daughter went into last year, 2023. I told her go to the same place. Hopefully you can understand this is this. Yeah, you agree it's the same place? It's almost the same time. Might be about 20 days here and there. We both went in summer. Can you see a difference? And this is not this is the Alex Glacier. This is actually a place called Egeshorn. It's a mountain there near the summit. You can see the difference, right? And that's 25 years approximately. Scary. Sea level is going up. The sea level is going up. It's gone up by about 10 centimeters over the last 20-30 years. Sea level is going up. What else is happening? The ocean is warming. And the amount of energy that is being dumped in the ocean is 360 zetajoules. Since that point, zeta is 10 to the 21. They need new SI units prefixes because the numbers are getting very large. I know it means nothing, but we'll compare it with something else. And this is actually much worse in the Indian Ocean. So this is IITM data, Roxy call. The Indian Ocean has been warming. The Indian Ocean has been warming from 1950 at 1.2 degrees per century, but that rate seems to be going up. Okay. Currently, it's projected, if we don't do anything, it's 3.8 degrees per century. It can be, it depends on how we are. There are different models. Okay. This is from a book chapter by him. Or his group. And this is not warming at the surface. This warming is happening down to 2000 meter deep. You're getting about 4.5 zetajoules per decade, which is going to go to about 20 zetajoules per decade in the future. Just remember, Hiroshima nuclear bomb is about 60 terajoules. Okay. And this is 20 zetajoules. So you can divide and find out how many bombs it is per day or something like that, continuously going on. That's the amount of energy we are dumping in the water. The sea temperature is going to go up. The sea temperature goes up, there's a lot more water evaporating. It has to come down as rain somewhere. the heat, I mean, yes, energy is going in. Okay. So now the sea temperature is increasing, and when the sea temperature there is, so the average sea temperature is something. The sea temperature goes up in summer, comes down in winter, all that happens. And there are also variations. Now, when it goes beyond the typical 90% level, you say it's a heat wave, it's a marine heat wave. The seawater temperature is very high. Right now, we have about 20 days a year when the marine water temperature is very high. This is projected to go up to about 200 days a year, which means almost permanently the sea is very hot. Which means everything, corals are gone. More important, the sea gets acidified because of carbon dioxide dissolving in it. Carbon dioxide is a very weak acid. So the pH of the sea is going to go down. If the pH of the sea goes down, it starts dissolving calcium in the shells and whatever else there are, calcium carbonates, starts dissolving them. So it affects marine life. It affects a lot of other things. Okay. So the Indian Ocean is being hit far worse than the average of the ocean thing that's going on. Okay. Then you have extreme variability. 2022, we had a very bad heat wave in summer, especially North India. And this was the like satellite map. Now with satellites, you can see, you can measure things. You can measure surface temperatures. This is around Delhi, 5th May 22 at 11:46 p.m. There are regions that are getting, this is like urban heat islands. The way we have constructed our cities, they get very, very hot compared to the neighboring regions. Though they are getting the same amount of sun, but the cities are getting extremely hot. Okay. Then there is also variability in rainfall. Now, what is happening is the average rainfall seems to be a very small amount. 0.4 millimeters per day is the difference. The average rainfall has sort of gone down, but the number of extreme rainfall events has gone up from the 1950s to now. The extreme events, a lot of rainfall in a suddenly happening has gone up, and this is happening pretty much all over India. The strange thing is there are regions where it's going down, going up, right next to each other. So it's very, very variable, and makes it very. This modeling is extremely difficult. I'm not the expert in it. Again, you can look at the tropical meteorology pages. They explain how they do this modeling. But the prevalence of these extreme events is increasing, and it's increasing all over India. Then, if this is your average sea temperature, sea surface temperature is about 28, 29 degrees, it's going up. Okay. Now, this is the 90th percentile. So 90% of your time, your sea temperature should be below this. This is data from 2020 when the sea temperature is much more above this, much above this. Because of this, there is when the sea surface temperature is very high, there is lots of water being evaporated. That leads to formation of cyclones. And this is when the cyclone Amphan happened. Okay, so the reason you are seeing more cyclones, which somebody said in the beginning, is because your sea temperatures are getting very high. And the amount of energy in these cyclones, these are some calculations. The Arabian Sea, pre-monsoon, post-monsoon, this is a 30-year period before and current, etc. Currently, there is much more energy in these cyclones. So the cyclones are getting more energetic. And that even the recent hurricanes that happened in the US also show that there are much more intense hurricanes. You did not have so many category 4 and 5 hurricanes all the time. So do we agree that there is a problem? By now, I hope you agree that there is a problem. That anthropogenic climate change caused by us, caused by human activity is real. Unfortunately, the story is complicated. Whose problem is it? Everybody. Everybody on the planet is affected. Who is responsible for this? Good question. And whose responsibility is to fix it? And this is where it gets beyond just science. I don't want to get into this, but I'm going to show you some things. Okay. So if you look at the period from 1751 to 2017, cumulative, who has put out carbon dioxide in the air? That is the US, that is Europe, that is China, that's India. This is in billions of tons. Okay. And then you can look at the distribution of various countries, etc. This is the cumulative amount of carbon dioxide put into the air. Now, how has it been changing with time? And you can go to Our World in Data is an excellent site. You can go and you can actually play these things and it'll show you how it is. I just took a screenshot. You can play these simulations or whatever they have. So you can see that initially, of course, in the 1750s, there's only Europe, there's only UK, which is basically, being giving it, we have data from. The US starts around 1770 or something like that. The US goes, the US starts somewhere there, that's the US amount. China has started much later, coming up here. Of course, the UK is going down, India is slowly rising over here. So these are the yearly amounts that you see. These are yearly amounts, right? Because this is per year. This is the earlier was a cumulative amount. Now you're looking at the yearly amount. This is the yearly amount that is going here. So who is emitting the carbon dioxide? Now, if you look at 2000 to 2020, the recent, this 21st century, this is China. China is currently putting out the most carbon dioxide. That's the US. That's it. India's here. India is increasing very quickly. The rate of increase in India is high. This is total amount. However, look at it per capita. Look at it per individual. That's the US. That is India. Okay. Well, China is there as well. But yes. Is there a question? Okay, not immediately. Let's go on. Okay. And I just wanted to say that, you've seen suddenly China come up. And everywhere, see, we have to improve the quality of life. We have to improve infrastructure. Today's civilization, we don't build things with stones. We build things with concrete. Okay. Cement and concrete are the stuff that makes up the world today. And this is a slide from a different talk. Cement was available right from the 1st century BC. This is the first building, Pantheon in Greece. It's built out of concrete. And, you have seen these massive buildings, Burj Khalifa, world's tallest building, right? The Three Gorges Dam in China. How much concrete do they use? Okay. The Burj Khalifa uses 0.33 million meter cubes of cement. A meter cube is 1,000 liters. This is 0.33 million meter cubes of cement. The Three Gorges Dam is 28 million meter cubes of cement. Okay. In 3 years, between 2011 and 2013, China used 6.6 gigatons of concrete. And that is, the US, you've seen pictures, you've seen the US developed country, all these highways, tall buildings, everything. 3 years in China used more concrete than the US used in the entire 20th century. If you want to make progress, you have to have concrete. That is what you build your civilization on. You built it 100 years ago. You can't stop me from improving the life of my citizens right now. However, cement making is one of the most carbon intensive activities. Why? How do we make cement? We start with limestone, calcium carbonate. We heat it. You heat it how? By burning something. You burn something, you have to heat this to break it up. To break it up into what? Calcium oxide and carbon dioxide. So you release carbon dioxide because of this, and you release carbon dioxide when you break up that carbonate and take that carbon dioxide out. So cement is one of the 8% of the world's emissions are due to just cement. However, if you need to build infrastructure, you can't do without cement. Okay. Now, this is again 1990 to 2018, now sort of recent. Carbon dioxide emissions per person. Saudi Arabia is the number of people, it's a small place, countries are, it's because they just use oil as if it's water or whatever. But, again, if you look at, this is of course population. So this axis is population, the wider it is. So this is where we are. India is actually the climate change performance index, which looks at how much are you polluting, what is the greenhouse gas emission that you have, how much renewable energy do you use, how much of your energy mix is renewables, what is your energy use like, what are you using energy for, right? And then of course, do you have a policy on climate? They have all these political accords. There is a Paris Accord and there's a Kyoto Protocol, etc., etc. So every country is supposed to be reducing their things by a certain amount. Okay, there's only one country that has walked away from this, which is the US. When Trump was there, they've again joined, thankfully. But they have some targets to meet by 2030, and so far, actually, we are not doing too bad on this. Given that we have to take into account that our starting level, the infrastructure that we have is not sufficient for the number of people we have. So we need to do two things. So now I want to get away from the sort of issues about climate politics and get back to science. Okay. So the last few slides, I'm not an expert, please. This is all economics, politics, social things, whatever. Let's not get into it. Let me go back and see if I can use some basic scientific principles to understand what is going on. Okay, without getting very technical. So many of you who are probably, have done this in college or something might know more details, but I'm trying to keep it very simple. Okay. So what do we want to do? Now, the story of climate change is effectively the story of energy balance. You cannot violate the law of conservation of energy. If you use energy somewhere, it has to go somewhere else. And it is a story of competing time scales. In what time do you do something? And then you'll see this coming up. And just remember that you cannot escape the laws of thermodynamics. The laws of thermodynamics are not laws that can be proven. They are observations, but they've never been, nobody has ever seen the law of conservation of energy being violated. Seen heat flow from something that is colder to hotter, the second law of thermodynamics, like entropy and things like that. So you cannot escape the laws of thermodynamics. Now, some things in this discussion, there are some terms which will keep coming up. There will be something called black body radiation. There will be things called greenhouse effect, radiative forcing. These are terms you hear. Global warming potential, things like this. So I want to make sure that we understand some of these very basic terminology. Okay? Any questions so far? No. Yeah. Okay, we'll take it at the end. So the first thing I want to do is black body radiation. Now, any object which has a temperature, a finite temperature, not an absolute zero. You, me, the sun, the earth, planets, stars, whatever. Any object which has a temperature emits some radiation, thermal radiation. This is electromagnetic radiation. If it's extremely hot, it could be even X-ray hot and emitting X-rays, some stars. It could be the universe as a whole, which is cooled from the background and is emitting microwave radiation, 3 Kelvin radiation. It could be your, some gas stove. It could be whatever. Now, things need not be perfect black bodies, but often they are very good approximations to a black body. What is a black body? A black body is something that sort of absorbs all the light that falls on it and can re-emit in all wavelengths, given the temperature it has. And this is how it looks. For a particular temperature, so if you are at 3000 Kelvin, 4000 Kelvin, 5000 Kelvin, forget classical theory and all this, the curve looks like it goes up, it has a peak somewhere, and then it gradually goes down. This is the shape, yes. Yes. If the question is, will you emit even if you're surrounded by a higher temperature? Yes. If you are at a finite temperature, you will emit something. You will absorb from that whatever is coming in, but you will emit at the temperature you are at. Okay. Now, there are three things. One is the shape of the curve, it's called the Planckian distribution. Max Planck worked out the physics of this. And you have a peak somewhere. The curve has a peak. Okay, so this is the visible range of the spectrum. So the visible range is peaked around 5000 Kelvin. Now, 5000 something, you can forget the 273. I mean, centigrade, Celsius, Kelvin thing. The peak depends inversely on the temperature. And if you've been in college and studied some physics, there's something called Wien's law, that the peak wavelength is inversely proportional to temperature, right? Also, as you see, 3000 was here, 4000 was here, 5000 is way up. The area under the curve is something like the total amount of energy that's been emitted. The total energy emitted depends on the fourth power of the temperature, not temperature squared, but temperature raised to 4. So very strong function of temperature. This is called the Stefan-Boltzmann law, but right now we just need to know its fourth power. So it's a very strong function of temperature, the total amount of energy that you're going to radiate. That's what we need to know for black body. Now, how does the sun look? If you are outside the atmosphere, so outside the earth, around where the earth's distance is, 1.5 million kilometers from the sun, the yellow curve is what is the spectrum of sunlight. The gray line here you see is an approximation to a black body. A black body at around 5778 Kelvin is what the sun is, and this is a very good approximation to the sun. Now, on Earth, what we get is the red curve. The red curve is again a similar shape, but it has these little tips because of the atmosphere. Some molecules in the atmosphere absorb some of these light, these wavelengths selectively, and hence you get tips in there. Also, you notice that this curve ends very abruptly here. We don't have much in the ultraviolet. That's because of the ozone layer. The ozone layer blocks the ultraviolet from reaching the Earth. So there is all this UV, and this is a very dangerous region of the UV that would harm us, but that is blocked off because of the ozone layer that we have. Okay, this is the solar spectrum, and we will use this later on. Now, what is a greenhouse effect? Please note that it's, greenhouses come from this, where you grow plants and all, you keep it warm. Okay, the greenhouse effect on the Earth is that you are getting some energy from the sun, which is heating up things on Earth. The Earth is going to be getting heated up and re-emitting that light. The re-emitted heat does not go out, stays in. Why? Because of absorption in the gas, which is very different than what a greenhouse of plants does. In a greenhouse of plants, you generally put glass or plastic or something just to prevent air currents. It would be air convection which would remove the heat. Okay, but here this is re-radiation from the Earth getting absorbed in the air and not going out. That is the greenhouse effect. Now, this, people will talk about short wavelength this way. Now, you have seen this red curve before. This is the sun spectrum. This is the approximate greenhouse, the black body kind of curve. Now, what is happening? The Earth is getting heated up. If the Earth gets heated up, the Earth is re-emitting infrared. This is the infrared that the Earth is emitting. In the atmosphere, this is the real total absorption of the this is ultraviolet, visible. Most of this is happening in the infrared. In the infrared, there are many molecules that absorb. There's water, there's carbon dioxide, there's oxygen, methane, nitrous oxide, etc. Okay, scattering from dust and all is not very important. That's happening only in the visible and in the. This is the stuff that gives you blue skies and red sunsets and all that stuff. Don't worry about that. But most of the absorption in the infrared is because of these molecules like water, carbon dioxide, oxygen, etc. Water is doing most of the absorption. Most of these dips are because of water. Water is there, water is absorbing. Carbon dioxide also absorbs a lot. So depending on where this thing is, which are the gases which are absorbing, we'll come to this a bit in detail when we discuss why is carbon dioxide becoming. Okay, so we have this is the sun energy coming in, heating the Earth. Earth puts out, is emitting energy. Again, depends on the temperature of the Earth. This curve will shift a little bit. Okay, and that can be absorbed by the gases in the atmosphere. So far, so good. Great. The greenhouse effect is not new. The fact that there is one of the polymath, great scientist, early 1800s, Alexander von Humboldt. He wrote a book in German, Cosmos, Translational Sketch of the Physical Description of the Universe. That's the book, translation. The translation is available in 1849 itself. Darwin called him the greatest scientific traveler who ever lived. He traveled the world, he went to South America, he went to different places, observed the climate, observed the plants, trees, animals, whatever, made notes, okay? And he introduced ideas of ecology, which led to ideas of environmentalism, etc. And he's called the father of ecology and environmentalism. And he also noticed that local impacts on development would cause human-induced climate change. This is 1830s. The first experiments are done in the 1850s. And this is a paper which links carbon dioxide and global warming, 1856, by a lady, Eunice Foote, who does experiments in a chamber with the sunlight, putting air in the chamber, carbon dioxide in the chamber, measuring temperature rises, etc. In fact, it's clearer. This is the original thing, but people have. So she does in air and in carbonic acid gas. Carbonic acid gas is basically carbon dioxide. Okay. And she says that an atmosphere of carbon dioxide would give to our Earth a high temperature. And as if suppose at one period of history, the air had mixed with it a larger proportion at present, an increased temperature must have necessarily resulted. So she's correlating the carbon dioxide in the air with the temperature. She publishes it in the American Journal of Science and Arts, 1856. There's a, these are all learned societies that used to publish these journals. She's not allowed to present that because she's a woman. In those days, somebody else had to read the paper for her. But anyway, she did these experiments and found that carbon dioxide is indeed linked to global warming. Okay, back to the present time, and we're going to start calculating. Okay, so we need to calculate some numbers so that we can make sense. So the first thing we're going to calculate is what is the temperature of the earth. Okay, now this is, I said, it's all about energy balance. So we're going to balance the energy we're getting from the sun and the energy we're going to put out. Simplest model possible. I will try to do it here. They've removed all the whiteboards. If we can't do it here, later on I can try, and this is apparently a smart board where I can write, I can solve it for you. So imagine that there is a star, the sun. Orbiting the star is a planet somewhere at some distance far away. At this distance, it receives some energy from the star. If I know the amount of, I know this curve, remember, we've seen this black body spectrum. We can approximate it as black body and all this stuff. So if I know the energy being put out by the sun at this distance, I can tell you approximately how much is going to be absorbed by the earth. And that calculation also we can do. What we can do is, this is now your planet. It has certain radius r. Now, just imagine the planet is actually a sphere, but it's absorbing the energy from the sun. Effectively, from the side of, if I look at it, it's like a circle. Yes? So the cross section of thing which is absorbing energy, let's forget what energy, some part of it is coming at an angle, all that. But simple approximation, it is this cross section that is absorbing energy. So the absorbing energy area is pi r square, area of a circle. Okay? Now, because of this, we will make another assumption that the whole planet gets to some temperature. Now, since it is at some temperature, it's going to start radiating energy. Now, clearly the temperature will rise, it will keep rising till it balances the energy that's being radiated out. So if I equate the energy coming in with the energy going out, I can tell you what the temperature of the planet is. So far, so good. Now, the energy that is going out from everywhere. Yes. No. See, why is it not the question is what is the area that is absorbing the energy? First thing, remember, the sun is only coming from there. The backside is getting no energy. And not every part of this surface is perpendicular to this energy. Okay, here it is perpendicular. Here it is almost at grazing incidence over here. So it will absorb much less energy here compared to this place. So the simplest approximation I can make is that this is going to be just the energy of a disk that is facing the sun. That's an approximation. We are trying to work out a very simple model. We will add complexity to it slowly. So if I have, suppose I have this, imagine this is a sphere, right? To you, it looks like a circle. The curvature of this, you're not seeing. From 1,000,000 kilometers away, this is just a circle for you. So pi r square is what is absorbing the energy. But once it is heated up, all of this is emitting energy. So the energy that is being emitted the area emitting is the entire area of the sphere, which is 4 pi r square. Okay. Now we add a little bit more complexity to this. Now, this surface may not absorb all the energy. There are clouds, there is something, some light is going to reflect it back. So the people in geology call this albedo, reflectance. So we can say that energy comes in, but maybe 30% of it gets reflected, or 35% gets reflected, something like that. Some amount of energy is getting reflected, only 70% is getting absorbed. Okay. So we can put one fudge factor that there is a reflectivity. Similarly, the fact that all these things are going to be radiated as efficiently as a black body may not be true. So we can say that it's not going to be, there's some constant t to the 4, it will be some multiplied by 0.8, 0.9, because it's not 100% efficient. So we can put what is called emissivity into the thing. So we can put some numbers to fudge for it. Now, if you put in all these numbers, that you are getting at the where we are at the Earth, we get about 1400 watts per meter squared. So if we have 1 meter by 1 meter surface, 1400 watts is coming on it. You have emissivity of 0.9, albedo of 0.3. The equilibrium temperature comes to be minus 18 centigrade. The temperature of the Earth should be minus 18 centigrade. We know it's not. So our simple model is not correct. And it's not correct. There are going to be many reasons it's not correct. One, maybe the Earth is generating its own heat. Now, there are radioactive materials in the core. They might be disintegrating and generating some heat. In some planets, this is important. Jupiter, for example, generates much more energy than it gets from the sun. Jupiter, internal energy generation is more important than the energy. It's much hotter than it should be at the distance it is. So there's something happening inside Jupiter to generate heat. In the Earth's case, what we have ignored is the atmosphere. It's the atmosphere which is not making it minus 18 degrees centigrade. And to understand that, we need to take a journey through the Earth's history. Okay? Not just the history that we see in the history textbook. What I call big history is history on geological timescales from the formation. Okay? So now, there is a Big Bang and all that stuff. But let's start at the Earth is formed 4.5 giga years ago, is a billion years ago, 10 to the 9 years ago. Okay? So 4.5 billion years ago, the Earth is formed. Okay? And then at this period, the solar system is very unstable. There are lots of things moving around. There is something called the late heavy bombardment that happens. Let's not get into the details of this, but lots of things are colliding with the Earth. The Earth is still not fully solidified. Magma is spilling out everywhere. Okay. All this is releasing. There's a lot of volcanism that's happening. Volcanoes are getting these collisions, etc. Massive amounts of greenhouse gases are being released. There's a lot of carbon dioxide, hydrogen sulfide, methane, etc. that's being released. And this is trapping the heat of the sun. Around this point, somewhere around 4 billion years ago, comets, asteroids, whatever, they are bringing water. They're bringing water to Earth. So the water that we have has all come from these asteroids and comets. Just remember, we did this calculation. The sun alone does not provide us enough power to have water in a liquid state on Earth. If there is no liquid water on Earth, life as we know would never happen. You need the greenhouse effect. You need this greenhouse effect to ensure that you had liquid water on Earth. Soon after, life is going to start. It starts in these pools and everything with self-replicating molecules, probably RNA type things, most likely starting around places where volcanic vents are happening under hydrothermal vents as they're called. Many people believe these are probably iron sulfides, nickel sulfides, which are catalysts of these reactions that are happening. But eventually packets of these things are forming. They form what are called liposomes, etc. By about 3.5 billion years ago, we know that there is this last universal common ancestor from which all forms of life have evolved has happened. This is all happening in water. Then life takes one very big step. Can we harness solar energy, not indirectly through the energy which is there in the rocks and all that, but directly from the sun? Can we harness solar energy inside the cell? Some cells develop a mechanism of doing this with chloroplasts. These are going to use sunlight, carbon dioxide, water to make glucose. Now I have a new way of harnessing energy from the sun directly. What happens? This process releases oxygen. Up till now, there's no oxygen. This process releases oxygen. And this, slowly, the atmosphere gets filled with oxygen. In a way, this is good. Some of this oxygen goes up, intense sunlight, it forms ozone. Ozone blocks the ultraviolet. Because it blocks the ultraviolet, it allows these life forms which are photosynthesizing to leave that water and get onto land. Now, this life which can do photosynthesis comes on land. In the next billion years, lots more oxygen is getting produced. Oxygen is an oxidizing agent. This is the first major extinction that's happening. Air gets oxidized to carbon dioxide. Carbon dioxide is not as efficient a greenhouse gas, it's less potent. The earth starts cooling down because carbon dioxide is also being absorbed by these plants. Plants are dying, the carbon dioxide is going back in the earth. Carbon is being removed from the atmosphere, methane is being oxidized to carbon dioxide is getting used up, the earth starts cooling and the temperature drops to -50. And here you have the real big ice ages that happen. Yes. So this is about 3 billion years ago, 3 giga years ago, 3 billion years ago, cycles. Then eventually from about 2.5 billion to about 0.6 billion years ago, life again evolves, prokaryotes, more complex forms, eukaryotes, multicellular life. Life is evolving. Okay. And around 500 million years ago, now from billions we're going to millions, 500 million years ago, there is what is called the Cambrian explosion. There is a time where lots and lots of diversity of life forms happens. These trees break up into many different things. There are whatever reptiles and this and that and arthropods and things. So life evolves. Now the carbon cycle is getting more complex. Earlier you had carbon in the atmosphere being consumed up somehow. Plants are depositing their carbon. Now you have animals. Animals are either eating plants or animals are eating animals who eat plants. So there's a lot more complex carbon cycle going on here with the thing happening. Nothing much happens until about birds evolved, dinosaurs evolved, mammals evolved 300 million years ago. Then there is another large extinction event 66 million years ago. It used to be called KT event, Cretaceous Tertiary. Now it's Cretaceous Paleogene extinction. 95% of the species are wiped out. We believe it's some asteroid that hit or something, whatever it is. Right? 95% species are gone. Small animals survive. The mammals survive. 10 million years ago, the first apes, primates arrive. 8 million years ago, the first human ancestors arrive. 2 million years ago, now a big change happens. Early humans discover fire. And that is a very big development. Very, very big development. Now from billions, we've come to millions, and now 2 million years ago, we've discovered fire. Fire changes things. Now, instead of just earlier photosynthesis happening, then you started eating plants. Now you can burn plants. You can burn wood. You can burn plants. Again, you're changing your carbon cycle. Because of fire, it allows humans to kind of dominate the planet. Fire gives you light. You're no longer limited by night and day. You can work at night. It gives you safety. It allows you to cook food. It reduces infection because you're eating cooked food. Humans develop at a faster and faster rate. Fire. Okay. Now, then humans are evolving so much that there is this megafauna, woolly mammoth, and think of these massive animals. They all die out. That's around 130,000 years ago, 8,000 years. All these big life forms die. Agriculture starts 10,000 years ago. The first civilizations were about 5,000 years ago. Now people, since agriculture developed, people are cutting forests, burning forests, cutting them, whatever, spike in greenhouse gases again. Okay? Because farmlands are not going to absorb as much carbon dioxide as forests. 3,500 years ago, somebody discovers, or some civilizations discovered, it's not one person, right? These things happen all over the world, that there is wind. And these moving gases, why are wind currents? Because it's solar-driven pressure gradients in the atmosphere. I can use it to get a sailboat to take me places. Once I have a sailboat, I have efficient global transportation. Earlier I had to walk to go places. Now I have a sailboat. I can go from continent to continent. Things move. Humans expand. This is indirectly solar energy. The pressure gradients are happening because of solar energy. Fire. Around 1,000 years ago, somebody, this is moving gases, the natural winds have to take you somewhere. Around 1,000 years ago, somebody figured that I can boil water and make steam. And I can use these hot gases. I can generate gases which can move things. But it's a toy. It takes about another, 1,000 years or so before somebody puts that hot gases and makes a steam engine. Now you have two things. I can have hot gases move things. I have engines. Around 900 AD CE, somebody discovered gunpowder. Now I can make hot gases, put them in a tube, put a projectile and something. Now humans can dominate other humans as well. So by 1500 CE, there's steam locomotion, in the sea, on land. All this needs something to burn. You have to burn something. The Industrial Revolution has started. Soon after this, I need to generate electricity. To do this, the carbon cycle has just thrown totally out of whack now. Why? What have we done? Now that earlier we were burning wood, plants that had died, trees that had died recently, we are burning them. Now I need so much carbon to burn that I have to dig up coal. Plants that died 300 million years ago, I'm digging them up and burning them, and that carbon which would have remained in the ground for millions of years is now going in the atmosphere. Right? So the energy demands that I have is much more than what I can directly get from the sun. Okay? And we are now using solar energy which was stored in the lives of dead plants and dead animals as oil or coal or whatever. We are using this. And just remember that the last 50 years is 0.003% of human history and 0.000001% of the Earth's history. And folks, we are now in the Anthropocene. That's it. So, just remember that the Earth's carbon cycles operate over millions of years. Obviously, there are time scales. The balance is the energy balance and the balance of time. It takes 300 million years for you to form that coal. I can dig it out in 50 years and put it out in the air. The Earth can't recover so fast. So if you look at this is like a log scale, okay? So this is the last 20,000 years, the last 100,000 years, the last 500 million years over here. So the Earth's temperature has been swinging. This is the KT extinction 65 million years ago. All that, this is it, and now suddenly your temperature is going up over here again. Right? Please remember, on the scale of the planet, human species don't matter. The planet will figure out how to do itself, but it'll take a few million years to do it. Something will happen, it'll go up and down, events will happen, but it takes hundreds of millions of years, if not millions of years. And if you look at this carbon cycle which is there, the carbon cycle, what does it do? Where do you have carbon? This is again a decade's worth of data. You are putting in carbon in the air, like about 9.5 gigatons of carbon in the air. There is also a little bit of carbon, 1.6 gigatons coming from land use change. If forests are going to get cut down, absorption of carbon dioxide is something that's effectively putting 1.6 gigatons of carbon, which otherwise would have been sucked in, is not being sucked in. So that's the additional contribution. Land uptake is around 3.4 gigatons. 2.5 gigatons are dissolving in the sea. Okay, and there are very much smaller things that are happening. There are a lot of stored. There is stored carbon. There is stored carbon as coal. There is stored carbon as oil, as gas. Right. In soil, there is a large amount of dissolved inorganic carbon in the sea. These are carbon stores. What are we doing? We are taking it in, but not the same amount is being. So there is an imbalance. The imbalance is 5.5 gigatons of carbon. Okay. Now, the Earth's cycles have a long time, which I've told you. Yes, please. Sure, I can go to the previous slide.
absorbing carbon dioxide. Because normally water and carbon dioxide are.
But seawater has plankton, there is life in seawater, right? Carbon dioxide is a little bit soluble, that will still happen, but there are organisms that will absorb carbon dioxide. Shells need to form calcium carbonate, that's going to absorb carbon dioxide. So there are lots of other people in the sea who's going to absorb carbon dioxide. It's not just carbon dioxide dissolving in saltless water, I mean in normal water. So that's what's happening. Okay. Now, Susan Solomon, who was basically well known for her work on the ozone hole and the Montreal Protocol and all that, they have also been calculating, even if you stop emitting all the carbon dioxide today, the response is very slow. So this is carbon dioxide ppm. You reach some point and you stop. Depending on where you stop, it's going to take some while to come down. Your pre-industrial level is here, but it's going to take you, we are at 2020 right now, it's going to take you, more than 1,000 years for things to come down, even if you stop today. Similarly, the warming that you have, even if you stop, it's going to take a long time to come down. Okay. Because what you are seeing right now is the effect from the Industrial Revolution on. And the Earth's timescales are very long. But why blame carbon dioxide? There are so many gases in this thing. Why are we worried that carbon dioxide has gone from 300 ppm to 400 plus? 0.3% tha, 0.4% ho gaya, big deal. There are so many other gases. The atmosphere contains so many gases. And the answer is basically dance class rules for molecules. Okay. Now, in order to absorb radiation, light, heat, whatever you call it, electromagnetic radiation, I need to interact. What is happening? The light interacts with molecules that are vibrating or rotating or things like this. Okay. Light, IR light, infrared, whatever, heat, these are all electromagnetic waves. I need some kind of charge separation. I need somewhere there are positive and negative charges. Only then can I interact, can an electromagnetic wave interact. Now, most of our atmosphere is nitrogen and oxygen. Nitrogen and oxygen, N2O2, are two molecules, they are symmetric. They can stretch. There's no net change in anything. They're identical. So the center of charge is not moving. Right? They can twist, they can stretch, nothing will happen. Thankfully. Thankfully, our atmosphere is mostly nitrogen and oxygen. The symmetric molecules, nothing can happen. In order to absorb things, I need to go to the other molecules, water, carbon dioxide, methane, etc. These molecules have much more interesting modes in which they can move around. So, the next thing is the vibrational modes of carbon dioxide. This explains why is carbon dioxide a greenhouse gas. Carbon dioxide is a linear molecule, carbon, oxygen, carbon, oxygen. Think of it as three things connected by two springs. Right? Springs store energy, bonds store energy. Now, how can you move these springs? There is one way where carbon is fixed in the middle, the two oxygens are doing this. Okay. The carbon-oxygen bond is not, this is a case where electrons are shared, and if you move them apart, the electron clouds can move a little bit, but this is symmetric. There's no change. Nothing happens because of the symmetric stretch. However, you can do an asymmetric stretch where carbon is in the middle. So this one comes close, this one goes there, this one comes close. You can do this. Asymmetric. Symmetric stretch, nothing is happening. Asymmetric stretch, right? Net charges are getting separated. Light can interact with this. Or I can have bending motions. I can bend. The oxygens can go this way. Carbon remains where it is, but once the oxygen this way, there is now a dipole moment, or that's what it's called. There is you're separating charges. This can happen this way. You can also happen this way. So there are two directions in which it can happen. Two axes. It can happen this way, or it can happen this way. So there are two bending modes, and there's an asymmetric stretch. And this is what we need to worry about. This is your asymmetric stretch. This is your bending mode. This is the experimental spectrum. This is a combination of this and this. There are some ways you can get harmonics and all. So you will see a combination of this and this over here. So there's one more smaller mode here, but the main modes are this and this. And what is important is, where do these modes lie in that envelope that you saw of the sun spectrum? It turns out that these guys can absorb. Now, you have to ask yourself, what is global warming potential? So, carbon dioxide is our benchmark. Carbon dioxide is a benchmark. We take carbon dioxide's value of global warming potential over a 100-year period as 1. Okay. Methane is 25 times worse than carbon dioxide. If you have nitrous oxide, laughing gas, 300 times worse. The more complex the molecule, this is perfluorotributylamine, some fluorinated molecule. So you have these CFCs and other molecules, sulfur hexafluoride, etc. Those will be like, sulfur hexafluoride is 22,000 or something, right? Much higher. The questions are the following: at what wavelength of that spectrum does it absorb? How much of it is there in the atmosphere? Methane is much less than carbon dioxide. Does it have competition? Is there somebody else already there who's absorbing? Okay. And how long does it stay in the atmosphere? This is what is going to decide. Now, for example, there is so much water vapor in the air. Water vapor is also carbon dioxide is a linear molecule. Water vapor is already a bent molecule. Water vapor has a dipole moment, because of which we have hydrogen bonds and everything else. There is so much water vapor in the air. Water vapor is a very potent absorber of IR. You saw those big dips in the spectrum. They're mostly water vapor dips. Then why don't we bother about water vapor? We should bother about water vapor, no? There's so much of it, and it's absorbing like crazy. Question: why is nitrous oxide 300 times higher? Why is methane much higher? Why are halocarbons so much more higher? Well, the number of, I'll tell you some you'll think. Methane. Carbon dioxide had carbon, 2 oxygens. Methane has carbon, 4 hydrogens. So the number of possible modes of methane is much larger. The number of IR active modes that are there which can absorb this, can interact with IR, with your light, is much higher for methane. Sulfur hexafluoride or something has got 6 fluorines attached to the thing. Anyway, the sulfur fluorine bond itself at the start is going to have some moment. So even if without doing anything, it can probably some of these modes can absorb. But otherwise, 6 means there are many modes possible. A more complex molecule has several modes that are available to interact with IR. So the possibility of absorbing is much higher. Now, in some cases, it might happen that there is competition. I can absorb, but the wavelengths at which I can absorb, there is already carbon dioxide or somebody else who's doing the absorption, much more than me. Methane is 2 parts per million. Carbon dioxide is 400 parts per million. If methane is going to absorb exactly at the same frequency, there's already carbon dioxide which has taken it up, or water vapor has taken it up. So there's competition, which might actually reduce your global warming thing. There are other things which can decrease the temperature. Aerosols, sulfur dioxide, some sulfates, etc. They can actually just sort of absorb they're not going to get hotter. It's going to make the people have said, oh, we should spray some particles in the air which will absorb the thing. Kind of dangerous to do experiments which are untried out, because the problem is you do something, it may mess up somebody else somewhere else in the world. So you have to be very careful if we can. There are ethical concerns with something. Water vapor? Any ideas? Anyone online? Why? How come water vapor doesn't matter? It's a diatomic. It's got diatomic molecule. No, it's not triatomic molecule. It's got two hydrogens. It should have many of these modes. But it's not a it is greenhouse gas, but we don't count it in the global warming potential. How long does it stay in the atmosphere? One of the reasons some of these molecules are bad, once they are there for hundreds of years. A water molecule going up, lifetime is 10 days. 10 days baad it's down. It doesn't get a chance to do much. So water vapor can amplify the effects. Water vapor is needed to generate these cyclones and whatever, rain and all this stuff. So water vapor will amplify the effects of global warming. But water vapor by itself is not so much responsible because it doesn't stay in the atmosphere that long. Okay. I think we'll end here. So I hope I have convinced you. Climate change is real. Also, you cannot beat thermodynamics. You cannot. You have to respect energy balance. If you do, you pay a price, as you see. Now, what we didn't discuss is runaway effects. What can happen is you have many paths on which you can go. Sometimes you can land up in situations which are irrecoverable. For example, the planet Venus is a very good example. Same size as Earth, very similar, etc. Surface temperatures are 400 degrees and much higher, and it's gone. It's been like that for millions and millions of years. And this again is very simply explained because if you look at water, the latent heat, the heat that you need to evaporate 1 gram of water or 1 kilo of water is you need 2.3 megajoules a kilo. Sorry, this should be melting, not vaporization. This is vaporization. To melt ice, you need only 0.3 megajoules a kilo. So once you melt ice, if you can make that vapor, it takes a huge amount of energy to undo this. It is much easier to melt ice than to condense water. So once you have melted it, you may have energy for that. You will never have enough energy to get it back. So you can land up into this. Planetary timescales are long. I don't know if we can mitigate these effects and how, but I think this is the time I should stop and we should have questions and we can have a cool drink because it's hot. Global warming, of course. So let's first ask members of the online audience. If you have questions, please put them in the chat and I will try to answer them. No guarantees. I may not know everything, but hopefully I have planted a lot of questions or thoughts for reflection in your minds. Yeah, go ahead.
Jyoti is asking, mostly when we do physics, we have a background curriculum solution where we use that small effects. So how well do we understand the world of 2+ degree outdated in the background, or do you understand how to?
Well, I think again, the modeling the Earth's climate systems is very complex. I don't think it matters whether it is 1.5 degree or 2 degree or something. The number is not very critical. The point is, what is very well established is that it is a number that is causing huge, there are consequences to that number on the ecological systems of the Earth. Though I think today's modeling is probably good enough that at a large scale, if you're looking at these energy balances in terms of zetajoules and something, you may be off by a little bit, but you won't be off by much. So I think the modeling is very reasonable today. And what has improved in the last decade, we probably knew these problems were there. What has improved in the last decade is the ability of computation to tackle such problems and tell us what possible things are there, which way we go if we have 1.5 degree increase or 2 degree increase or 1 degree increase, or what is the limit to which we can tolerate something. The computational modeling has improved dramatically in the last decade.
Asking whatever may be removing changes, but it is constantly present. So why is it not like absorption spectrum of water having lower energy in the?
So no, the absorption spectrum of water is there. So the question is, even though the water vapor molecule goes up and lifetime is 10 days, it's coming down again, but other molecules are going up. So there is always some water vapor in the air. But yes, I think once your cycle is complete, this water cycle is happening on a much faster time scale than the other cycles. So its effect is not that dominant, and also it depends on the wavelengths at which it is. Maybe there are other molecules not there. I am not an expert in this, so I will find out and get back to you. Details of exactly this. Okay, then
there is a optimistic question. Can't we manufacture a device which would run on green energy and replicate the photosynthetic process, capturing and removing lots of carbon?
You probably could. In fact, carbon sequestration, I mean, trapping the carbon is one of the big topics and big markets and something else. The question is, can you do it at scale? It is easy to say that I can do, I have some, could be nanoparticles, could be a new understanding of photosystem 2, which is happening in a plant leaf, but I'll do it more effectively. I can do that in a test tube or something, bubble carbon dioxide and capture it. All these things make sense, usually at not 0.4%. If you have 0.4% carbon dioxide in air to capture it, difficult. If you put it at, say, a chimney of a power plant where it's, maybe 50% carbon dioxide, is much more effective over there to capture the carbon, prevent that carbon from going up by capturing it somehow. The question is scalability and economics. We probably know the solutions to some of them. The question is it economically feasible to do it? Are people willing to pay the price for it? That is the question, which is the main thing. The technologies might be there. Is it scalable? Can you do it on a gigaton scale? And is it economically worth doing it on a large scale? These are the questions that have prevented the deployment of it, in my understanding. For now, these are the questions. Before we stop our live stream, I would like to tell the viewers that our next few Chai and Wise, I can stop screen sharing. Yes, I should stop screen sharing. Okay, online audience, before we end the live stream, the next Chai and Why, which is 3rd November, we're going to do a series on the Nobel Prizes of the year. We are starting with the Nobel Prize in Medicine and Physiology, which is given for microRNA. That's going to be the topic of the next Chai and Why, Mayuri Rege at Prithvi Theatre. After that, the mid-November Chai and Why is here on the Nobel Prize in Chemistry, which is on AI backend methods for protein structure determination, etc. The December Chai and Why is, we'll announce, but mostly it will be the we'll announce. Yeah, many possibilities, but we will cover the Nobel Prizes next. Okay. With that, we will stop the live stream. If there are no more questions, let him do it, and then we can